Continuing our discussion on to probability, it's important that not only you know the probability and likelihood of flipping a coin and rolling a die, but also the likely outcomes of a deck of cards. So I've already put into your lecture notes a picture of a deck of cards. So if you're not familiar with a deck of cards, you would want to study what cards are in a deck, because there will likely be questions on your homework and on your midterm and final regarding a deck of cards. So if you don't already have a deck of cards, maybe you might want to purchase one or at least study the picture that's in your notes. But basically, a deck of cards is comprised of 52 total cards, and this is not including the jokers. There are two colors. There is black. These two are black, and these two rows are red. So that means there are 26 black cards and 26 red cards. Those black cards are broken down into suits. So the black cards, there are 13 spades, and there are 13 clubs. The red cards are broken into two suits. There are 13 hearts, and there are 13 diamonds. Now each of those 13 cards are broken down by number, starting with ace, which some people think of as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. The jack, queen, and the king are called face cards. So there are 3 face cards of each suit times 4 suits, so there are 12 face cards. So let's ask ourselves some probability questions based on the deck of cards. So a standard deck that has 52 cards, and we're going to randomly select one from the deck. Find the following probabilities. First, find the probability of randomly selecting a heart. So remember, it's always going to be out of 52 cards. So out of 52 cards, how many hearts are there? Well, from the picture above, count all of the hearts in the picture, and you'll see that there are 13 hearts out of 52. As a reduced fraction, this is the way your homework will always want reduced fractions like this. Unless it asks for a decimal, then you could give it as a decimal. Unless it asks for a percent, then you could give it as a percent. So all of these probabilities all state the same story. Fractions, we always reduce these ratios down to lowest terms. We can also divide those in our calculator to get a decimal, and we could always move the decimal 2 times or multiply by 100 to get the percent. How about the probability of randomly selecting a heart or a club? So the probability of selecting a heart or a club. Okay, so the probability of selecting a heart or a club. The first thing we need to do, since it's an or, I know I need to add the two probabilities together. So I know it's going to be the probability of selecting a heart plus the probability of selecting a club. However, I don't know if I'm supposed to subtract out that extra piece. We have to determine whether hearts and clubs are mutually exclusive. In other words, when I look at the Venn diagram and I have hearts over here and clubs over here, are they mutually exclusive, or do they share some cards in between? In other words, is there a card in the deck that is both a heart and a club at the same time? And the answer is no. They do not share any cards in common. So therefore these are mutually exclusive. So therefore all I have to do is add their probabilities together, and I don't have to worry about subtracting out the middle. So the probability of getting a heart, we just found up here, 13 out of 52, plus the probability of getting a club, well, that's another 13 out of 52. And when you simplify this fraction, you're going to get 1/2 of the deck, which we could write as 0.5 or 50%. So all of those would be okay. How about the probability of randomly selecting a heart or a club or a diamond? Well, just like the picture up here, hearts, clubs, and diamonds, well, diamonds would just be another event out here not joined by any of the others, because there are no cards in the deck that are both hearts and clubs, clubs and diamonds. They're all mutually exclusive. You can't have multiple suits on one card. Since they're all mutually exclusive, I simply just have to add the probabilities of each together. So the probability of getting a heart or a club or a diamond is going to be the probability of a heart plus the probability of a club plus the probability of a diamond. So it's going to be 13 plus the other 13 plus the other 13. In simplified form, well, hey, that's 3/4 of the deck, which is 0.75, which is 75%. At this point, I'd like to make sure that you're aware how to reduce fractions in your calculator. So for example, if I were to have done this question and I added 13 out of 52 plus 13 out of 52 plus 13 out of 52, if I use the fraction key right here instead of the division key, and when I hit enter, it will automatically reduce that fraction for me since I entered it as a fraction instead of as a division sign. How about the probability of randomly selecting a heart or an ace? So the probability of selecting a heart or an ace. Well, let's look at the Venn diagram. Here's the hearts. Now the aces, are they going to be mutually exclusive or are they going to be joined? In other words, is there a card in the deck that can be both a heart and an ace at the same time? Well, yes. There's actually one card right here in the middle, and that's the ace of hearts. So these are not mutually exclusive. So in order to OR their probabilities together, I have to find the probability of a heart plus the probability of an ace, but I have to subtract out the probability of getting a heart and an ace at the same time. Well, the probability of getting a heart is 13 out of 52. The probability of getting an ace is 4 out of 52, minus the probability that I'll get a heart and an ace at the same time. There's only one card that is a heart and an ace at the same time. So 16 out of 52 is going to reduce down to 4/13, which comes out to 30.8%. Another way to do this is to simply count the cards. So if you have the picture in front of you and I want to find the probability of selecting a heart or an ace, I could simply go up to my picture and count them all. Let's count all of the aces. 1, 2, 3, 4. Now let's count all of the hearts. Well, let's not count that one again. I've already counted that one. So that's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's 16 hearts or aces in the deck. And look what we have right here. There were 16 hearts or aces out of the deck. So some people that are more visual, if you don't like the formula way, you can count simply the cards. How about the probability of randomly selecting a 2 or a jack? Let's look at the Venn diagram. Here's all the 2s in the deck. Now the jacks, are they mutually exclusive or are they joined? In other words, is there any cards that are 2s and jacks at the same time? And the answer is no. There is no card that could be a 2 and a jack at the same time. They're separate numbers. So therefore, these are mutually exclusive events. So I have to just add the probability of getting a 2 plus the probability of getting a jack. There are 4 2s in the deck plus 4 jacks in the deck. So this is going to be a total of 8 out of 52. 8 out of 52, when it's reduced, is 15.4%. The probability of randomly selecting a face card or a diamond. Okay, so the Venn diagram, we have all the face cards here, and then we have the diamonds. Mutually exclusive or not? Ask yourself, is there a card in the deck that can be a face card and be a diamond at the same time? And the answer is yes. There are actually 3 of them. Okay, there's the Jack, Queen, and King, all of diamonds. These are not mutually exclusive, so I'm going to take the probability of the face cards plus the probability of the diamonds, but I have to subtract out the probability that a card will be a face card and a diamond at the same time. So the probability of getting a face card is going to be 12 out of 52. Go back and count them. Plus the probability of diamonds, there are 13 out of 52. Then we're going to subtract all of the face cards that are also diamonds, and there are 3 of them. So this comes out to 22 out of 52, which is 42.3%. How about the probability of not selecting an ace? So if here's all the aces, I want this probability that I won't select the ace, the complement. So to find the probability of the complement of not getting an ace, I find the probability of actually obtaining an ace and subtract that from 1. There are 4 out of 52 aces, so this is going to give me the other 48 cards in the deck, which comes out to, if we simplify the fraction, it comes out to 92.3%. The probability of not selecting a black card. So I want the probability of not selecting a black card. So that's going to be 1 minus the probability of selecting a black card. Well, 1 minus the probability of a black card is 26 out of 52 because there's half of the deck, right? So we're going to get an answer of 26 out of 52, which is the other 1/2 of the deck. Well, I probably could have figured that one out, because if I'm not going to select a black card, I'm clearly selecting a red card, and 50% of the cards are red. So this actually is equal to the probability of selecting a red card. Let's do another example. This time it'll come from a table. It says that the following data represents the number of speeding tickets issued to individuals in the past year and the gender of those individuals. Determine the probability that a randomly selected driver is female. So let's first go through the table here and just determine exactly what we're looking at. So I have the number of people with individuals in the last year who may or may not have received a there were 0 females that received a ticket, 1 female, or excuse me, there were 14 females that received 1 ticket, 97 females that received 0 tickets, 3 females that received 2 tickets, and 1 female that received 3 tickets just in the last year. So there were a total of 115 people that must have been pulled over. There were 82 males that were pulled over. 71 of them did not get a ticket. 7 got 1 ticket, 1 male got 2 tickets, and 3 males got 3 tickets in the last year. I could also add the columns. This tells me the total number of people that were pulled over that did not receive a ticket, the total number of people pulled over that received 1 ticket, 2 tickets, 3 tickets. What you're going to notice about this table is that these 2 numbers over here will add up to 197. These totals down here will add up to 97. Also, these numbers up here will also add up to 197. So when you're constructing a table, always make sure that those 3 sections of the table all add up to the total. Okay, so we're asked to find the probability that if I randomly, out of 197 names in a hat, and I randomly pull out one person's name, What's the probability that that person is female? Well, there are 115 females out of 197. So this is going to be the probability of a female. It's going to be 115 out of 197, which comes out to 0.584. Or as a percentage is 58.4% chance. So out of the total, there was majority of females that were pulled over. Not that received tickets necessarily, but majority of the people that were pulled over were female. Part B says what's the probability that the person has been issued one ticket? So it says nothing about gender. I just want to find the probability that someone received a ticket. Well, how many people received one ticket? There were 21 people that received one ticket out of the total. So this is going to be 0.107. What is the probability that a randomly selected driver has been issued at least 2 tickets? At least 2 tickets means they could have gotten 2 tickets or more. So I want to find the probability of 2 tickets or 3 tickets. And since these are mutually exclusive events, you either gotten 2 tickets or 3 tickets. You didn't get necessarily both. So I'm just going to add the probabilities together. So the probability somebody might get 2 tickets plus the probability that they might get 3 tickets. There were 4 people out of 197 that got 2 tickets, 4 people out of 97 that got 3 tickets. So when I add these two numbers together, you're going to get 0.041, which is 4.1%. What is the probability that someone is female or has been issued one ticket in the past year? So I want to find the probability of being female or one ticket. Well, these are not mutually exclusive because you can see in the table here that there are people that are female and received one ticket at the same time. There are 14 of them. So to do the formula method, I would have to add the individual probabilities of female plus one ticket, but then I have to subtract out the probability that they might be female and received one ticket at the same time. So back up to my table, what is the probability of being female? Well, we answered that in part A. That was 115 out of 197. Plus the probability of getting one ticket. Well, we answered that in part B. That was 21 out of 197. But if you look at those two totals, this 115, all of these numbers right here, this is all the females. And all the people that received one ticket is going to be all of these numbers right here. And you're going to see where those the row and the column intersect, which is this number right here, has been added twice. Because if you add all of these numbers and then add all of these numbers, you're adding the 14 twice. These are the people that are both female and received one ticket. These are the 14 that we have to back out of our equation. So we're going to subtract the 14 back out, and that's going to leave us with 122 over 197, which is 61.9%. How about the probability that a randomly selected driver is female with one ticket in the last year? So we're looking for the probability of them being female and receiving one ticket. Well, hey, I actually just did that. That was this answer right here. That's what it's asking for again. So the probability of someone is female with one ticket is 14 out of 197. 14 out of 197 is 7.1%. Another word for or is the union symbol. So if you see or the union symbol, these mean the same thing. I'll call this union. The upside down U is called the intersection, which I'll also call the and symbol. So what is the probability that a randomly selected driver is male or has 0 tickets? Male or 0 tickets. Again, just like this example up here, these are not mutually exclusive because there are people that are male and receive 0 tickets at the same time. So we're going to find the probability of being male plus the probability of having 0 tickets minus the probability of being male and having 0 tickets at the same time. There are a total of 82 males in the study. There are a total of 168 drivers that received 0 tickets. But then we have to subtract out the probability of a male and receiving 0 tickets at the same time, and there were 71 males with 0 tickets. So this is going to come out to 90.9%. Finally, what is the probability that a randomly selected driver is male or has at least 2 tickets? So I'm going to find the probability of being male plus the probability of at least 2 ticks minus the probability of being male and at least 2 ticks. Okay, so the probability of being male, we've already answered that question up here. There are 82 males on the study. Then we're going to add the probability of at least 2 tickets. Well, the probability of getting at least 2 tickets we found up in part C up here. The probability of getting at least 2 tickets is the probability of 2 tickets plus the probability of 3 tickets. So it's 4 out of 97 plus 4 out of 97, or 197. Minus the probability that someone could be male and received at least 2 tickets. So if I go back up to my graph, here's males in this row right here, and which of these males received at least 2 tickets? This people right here. There was 1 male that received 2 tickets, and there were 3 males that received 3 tickets, so a total of 4. So when we intersect or union the males with at least 2 tickets, we're adding this 1 and this 3 twice. So we're going to have to subtract out the 4 that were in that red circle, which is going to come out to 43.7%. All right, on to the next section, which is 5.3. We're going to now talk about independence. Independence of an event are considered if the occurrence of the first event in the experiment does not affect the probability of the next event. So they're 2 separate events. This is not the same as mutually exclusive. Mutually exclusive consists of 1 event. Picture picking 1 name out of a hat, and you're looking at that name and looking at 2 characteristics of that one person's name. Now we're talking about taking 2 names out of the hat, and whether what you pick for the first name affects what is going to occur or the probability of the next person's name getting called. Independence of 2 separate events. They'll be considered dependent if what happens on the first event does affect the outcome of the second event occurring. The multiplication rule for independent events is pretty easy. In order to find the probability that this event will occur and then this event will occur next, we simply just multiply their probabilities together. For example, let's first decide whether these events are independent or dependent. Your favorite color is blue, and your friend's favorite hobby is fishing. Those are clearly independent, because whether or not my favorite color is blue is not going to have any bearing on the probability that your favorite hobby is possibly fishing. They're completely unrelated events. However, in this next example, these would be considered dependent events, because whether or not your car runs out of gas is going to affect the likelihood that you might be late for school. So this is an example of independent versus dependent events. So let's look at some possible probabilities. First, let's decide why the following events are independent. What is the probability of obtaining 5 heads in a row when flipping a fair coin? So we're going to flip one fair coin 5 separate times, and we want to find the probability of getting 5 heads all in a row. Well, the reason these are independent is because no matter what I flip on the first coin, I'm going to flip it again, and I still have a 50% chance of getting a heads on the next throw. So no matter what I got on the last one, it's not going to affect what the probability is on the next particular coin flip. Since there's a 1/2 probability of getting a heads on the first throw, I want to find the probability that I will get another heads. So I'm going to multiply that by the next throw. Then I'm going to throw the coin again, and I want to get a heads another time. And then I'm going to throw the coin again and again. So I'm throwing it 5 possible times. Each time I have a likely outcome of 1/2 probability. If I multiplied all these together, a shortened way of doing it would just be 2 to the 5th power if you would like to make that a shorter possible calculation. This happens to be 1 over 32, which comes out to 0.031. 3.1% chance of flipping this coin and getting a heads all 5 times. Obviously, that is a very unlikely outcome. In fact, we would call that unusual. Refer back to the first page of the notes. An unusual event is an event that occurs less than 5% of the time. So I would definitely say that flipping a coin 5 times and getting a heads all 5 times would be considered unusual. Number 3, about 13% of the population is left-handed. If 2 people are randomly selected, what is the probability that both are left-handed? What's the probability that both are right-handed? So if I've got all 330 million people in the United States, and I know that 13% of them are left-handed, I randomly go into that hat of 330 million people and I select one name. There is a 13% chance that that person is left-handed. Now, I'm going to go into that hat of 330 million people and select one more name. Well, that person also has a 13% chance of being left-handed. So by multiplying those two numbers together, you're going to get a 0.0169, which is a 1.7% chance of selecting 2 left-handed people in a row. Very unusual, again. The second question says, what's the probability they're both right-handed? Well, right-handed is the complement of left-handed. So if you have a 13% chance of being left-handed, that clearly means you have an 87% chance of being right-handed. So I'm going to go into the hat, I'm going to select a right-handed person. Then I'm going to go into that hat again and select another right-handed person. This is going to leave me with a 75% chance of selecting 2 right-handed people in a row. Now you might be asking yourself, why don't these two numbers add up to 100%? So remember, I have this hat of 330 million people in the United States. There's an almost 2% chance of selecting 2 left-handed people. There's an almost 76% chance of selecting 2 right-handed people. They clearly don't add up to 100. So what outcomes am I missing? If you said the probability of selecting a left-handed and a right-handed, you'd be correct. We're missing the 2 outcomes of selecting a left and then a right, or a right and then a left. If you found out what those probabilities were, they would add up to 100. Let's go ahead and quickly do that exercise. The probability of selecting a left-handed person and then a right-handed person is 0.13 times 0.87. The probability of selecting a right-handed person and then a left-handed person is 0.87 times 0.13. If I put those into my calculator, I get 0.11 or 11% chance of occurring. So now, if I added up all of these probabilities, they will indeed add up to 100%. There might be a 0.1% of rounding error in there because these have been rounded, but they will be very close to 100%. So let's say I select a single card from a deck. So you have a deck of cards in front of you, and I randomly select one card from all of these cards here. Okay? And then my question to you is, I'm going to then put that card back into the deck. Then another card I'll randomly select. So I'm going to select two cards, but I'm going to replace the first one back into the deck. So what is the probability? They are both queens. So I go into the deck and I randomly select one queen. There's a queen there. So let's say I randomly selected this queen first. I pull it out and I say, okay, well, I had a 4 in 52 chance of selecting that first queen, right? Well, then I put that queen back into the deck. And then I go in, I shuffle them up, and I randomly select another card. Well, I still have a 4 out of 52 chance of getting another queen, and I might even draw the same queen again. So when I multiply those two numbers together, I'm going to get 0.0059. This is less than a % chance of happening. Very unlikely that that would occur. The female gender makes up 50.8% of the U.S. population. What is the probability that I randomly select 5 females to call on during my telemarketing job that I'm selling staplers? So I am going to make one phone call. My first event is making the first phone call, and I have a 50.8% chance of calling a woman. Then I make my second call. I have a 50.8% chance of selecting another woman to call. And I am clearly going to do this 5 times. Rather than multiplying this out 5 times, an easier method would be to just take this to the 5th power. This is going to get me 3.4%. You could do the math. What is the probability I randomly select 5 males? Well, it's not going to be the opposite of this because of the same reason that we said below with the right and left-handed people. All females and all males are not complements of each other. There are many more outcomes that are possible. We could select a male, female, male, female, male, 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 female, female, and so on. There are many more options. So don't just assume that this is going to be the complement. So the probability I'll select all males, I have to find the probability of selecting a male and multiply it by itself 5 times. So what is the probability that I'll select a male? Well, that individual probability is the complement of selecting a female. So the probability I'll select a male is going to be 0.492. And I'm going to multiply that by itself 5 times. So I'm going to have 0.492 to the 5th power. And that's going to come out to be 2.9%. So my question to you is, does the answer to 5 and 6 add up to 100%? And I already kind of told you why it does not. Clearly, they don't add up to 100%. In fact, these are both unusual events, both of these. It would be unusual to call 5 females in a row or 5 males. And the reason they don't add up to 100% is because there could be a combination of men and women I could call. Such as male, male, woman, male, woman, as one example.